So, any questions about the homework that's due tonight or anything else that's going on in the course? Now, the homework due tonight has animation in it, is that correct? It does not yet have animation, that's next week? Okay. The motion of a rigid of the square flying, that's next week. We have these extensive office hours in this class, which are not so well attended. I think perhaps the reason they're not so well attended is because we're posting the solutions before you hand in the homework. But we have these office hours for you to learn from, so we would like to encourage you to come to all the various office hours. And you need not have a question specifically about a homework problem. It can be any question about anything related to the class. Or you could try asking questions about things that are not related to the class. We put aside the time to talk to you, so come talk to us. Okay, ready to go on? Logistics questions, course stuff, background stuff, ready to go. Okay, so where are we in this class? We're trying to figure out how things move according to Newton's laws or Newton's and Euler's laws. The particular things we're looking at are particles and rigid objects, rigid bodies they're sometimes called. And now we're at the point of looking at general motion of a two-dimensional rigid object. And then later in the class, we're going to look at constrained motion of a rigid object. So just to give you this sort of a plot summary, if you look at things which are free, like particles, in 1 dimension, 2 dimensions, 3 dimensions, the equations are kind of easy. You have F equals ma, and if you want to know what happens in time, you write A equals F over m. You write the equations for F, the constitutive laws, the material properties that tell you the force in terms of the position and the velocity and the time, and you can calculate the motion. You can write that as differential equations to go forward in time. Now, rather than have things free where you know what the forces are, there are situations where objects are constrained. And when they're constrained, like the car problems, the sliding box problems, and so on, you can't just write F equals ma because you don't know the forces. The forces and the motion are coupled to each other. And those problems you have to simultaneously solve usually linear equations or do some trick by taking angular momentum balance about an appropriate point to get the motion of interest. Okay, so now we're in the same situation for objects in 2 dimensions. We're going to look at things flying around in 2 dimensions. And to start with, they're free. Well, they're not entirely free because the object itself is constrained to be a rigid object. So we figured out how to deal with the rigid object with this simple angular momentum balance equation. Once we figured out that constraint, how the Avogadro's numbers of particles are connected to each other, we have this free object. So what's the situation is we have some reference frame where we're going to write the laws of mechanics. We use script F for the fixed frame, Newtonian frame, the place where when we measure positions and velocities, it gives us an accelerations. Newton's laws are accurate. And we have some object which is flying around. And so here's our rigid object which is flying around. And sometimes we call this B for the body or object. Or it could have other names as well. And this thing is flying around. It's got some point which we're going to keep track of, the center of mass, important point for mechanics of rigid objects. And it has, relative to this frame, it's got some position, R of G relative to O, which we might just write as R if there's nothing else going on. Or we might just write it as RG, shorthand. Okay, as this thing spins around, we can keep track of its orientation. Best is if you keep track of orientation with a counterclockwise rotation. Otherwise, formulas involving cross product can give you negative of the answer you want to get. As this thing spins around, we can keep track of something we call the angular velocity, which is the rate of change of any angle we mark in the object. Now, as this thing flies around, we can draw a free body diagram of it, and the free body diagram shows all the forces which are acting on it, whatever they are, as this thing moves around. And from this, we can write the equations of motion, or the laws of mechanics. And what do we have? We have for this thing linear momentum balance, which says that the sum of all the forces, and it's not really all the forces, it's all of the external forces acting on this, is equal to the total mass times the acceleration of the center of mass. And if we want, we can rewrite this as the acceleration of the center of mass is equal to the sum of all the forces divided by the mass. And we can rewrite this as Vg dot is equal to the sum of all the forces divided by the mass. And then we can write R dot G is equal to Vg. And this then gives us equations from which we can calculate the motion. Now you can't use those equations to calculate the motion unless you know ways to calculate these forces. So these forces must be given in terms of, say, the position, the angle, the velocity, time, other things which you can know. This equation is correct whether or not we know this, but if we want to think of this as a crystal ball, something we can go forwards in time and figure out. We need to know the forces. So what would be examples is if I take something like this and I throw it across the room and I want to figure out how it moves. I know what the gravity force is. I could say there's some air friction force. If that air friction force, I had a rule for it, for say what the torque it caused as a function of the angular velocity, and the net drag force is a function of the velocity, then I would know what all the forces are and I could predict the motion of this thing. Now, if that air friction force depends on the angular velocity, this is not yet a closed system of equations. We also have to write the angular momentum balance equations. What are the angular momentum balance equations? It says the sum of moments relative to any point we like is equal to the rate of change of angular momentum relative to any point we like. Now, when in doubt in dynamics, if you're not inspired, like in those car problems and box problems, I taught you how to be inspired to pick special points to make the algebra easy. But if you're not inspired, and it's actually good to be not inspired for these free motion problems, use as the reference point for angular momentum balance this point G, the center of mass. And you can use that for the car problems and the sliding box problems too. There it makes more algebra, here it makes less algebra. So we can turn this into this h dot relative to g is just ig omega dot k for a rigid object. So we can turn this into omega dot is equal to the sum of moments relative to g dotted with k divided by the moment of inertia with respect to g. And we'd like to know these moments in terms of the position, velocity, angular velocity, the angle, time, etc. And then we also can write theta dot is equal to omega. And if we take this is how many scalar equations? This is 4 scalar equations. This is 4 ODEs. And this is 2 ODEs. So altogether, we get 6 ODEs for x, y, vx, vy, theta, and omega. Yes?
It's supposed to be h dot. Or is that
This is supposed to be h dot. Now, let me just give a simple example. Ballistics with no friction. So the free body diagram will look like this. Here's our object. We'll have our point G, and we'll have mg like this. And so this is the eraser going across the room, the one I just threw across the room. If we leave out air friction How does that move? Well, F equals ma is just like for a particle. So that tells us that xg is equal to xg0 plus vx0 multiplied by the time that goes by. It tells us that yg is equal to yg0 plus vy, or vyg0 times t minus gt squared over 2. And it tells us that omega is equal to omega 0, and it tells us that theta is equal to theta 0 plus omega 0 t. So we have, for the 6 ordinary differential equations, we have to have 6 initial conditions, which are the initial state, the initial position and velocity. Position is x, y, and theta. Velocity is vx, vy, and omega. If we're given this eraser's initial position and velocity, we can figure out how it moves for all time by just solving the differential equations. And these things give those solutions to the differential equations. Why? Because the F equals ma equation is exactly the same as for a particle, and you know how to solve that one. And the angular momentum equation just turns into omega dot equals 0. Because there's no moment of the force about the center of mass, because the only force is at the center of mass. Or all of the gravity forces on the rigid object are statically equivalent, they're equivalent or equipolant to a single force at the center of mass. The gravity force has no net moment about the center of mass, so the angular velocity is constant. Now there are more complicated problems we could do, we could spend time on, and you could maybe think about them, like what's the motion of an airplane if you put lift and drag forces on it. Once we figure out the rules for the lift and drag forces on the wings, then we just plug in these equations and we can figure out how an airplane moves, at least without control. Okay, any questions about this? Anybody want me to repeat any part of what I said? Anything look ambiguous? This is simple, right? This is simple the same way that particle motion, when it's not constrained, is simple. You just write F equals ma. Here we just write F equals ma. M equals I alpha. This is the equation m equals I alpha, or J alpha. And you switch it around to write the differential equations and solve them. Okay, now one-dimensional mechanics was easy too, until we added constraints. And now we want to add constraints to this system. So here we have general motion of this rigid object in 3 dimensions. This has 3 degrees of freedom, DOF, degrees of freedom. What are those 3 degrees of freedom? They're x, y, and theta. And they're all free. That's what you mean by degree of freedom. What we'd like to do now is we'd like to add constraints. So we're going to have complicated motion, perhaps, but it's not going to have all of these 3 degrees of freedom. It's going to be more restricted. And to do this, I'm going to just start with an example, and I'm going to give you a quiz problem about an example. And I didn't show you how this goes, so it's not like I'm expecting you to be masters of this stuff already. So I'm going to give you this quiz question. Some of you will have seen this quiz question before. It's kind of a famous quiz question. So if you've seen it before, just keep it to yourself. Don't yell things out. And if you want to talk to your friends about this problem, if you've seen it before and you know how it works, don't tell the person next to you that you know how it works. Just try to convince them of what's going on. So this is the movie. The movie is called Heat Treatment of Aluminum. And we can verify that that's the movie. If you read the small print here, it says Heat Treatment of Aluminum in the title frames and so on. And we can learn from this movie. And we're going to learn the following way. I put this movie on this table here like this. And what I'm going to do is I'm going to pull gently on this film. And the question is, when I pull gently on this film, what happens? I'm not going to pull hard. I'm going to pull gently. Does the film come this way? Does the film go that way? Or does it stay still? Or something else? Now, I don't want you to raise your hand. This is a quiz question. Just out of curiosity, I'll let you raise your hand, but I don't want to yell out answers. How many people have seen this puzzle before? Raise your hand. Now, why so many of you did? What?
It's fun.
It's fun. Okay, well, it's okay. Some of you didn't see it, and you can think about it again anyhow. So, okay, talk to each other, figure out the answer. Okay, 1 minute more. You can do it theoretically, you can do it any way you want. I'm actually going to do the experiment. I can't see how many people voted without showing you the answers and so on. How many people want more time to think about it? Okay, 15 seconds more. Five, 4, 3, 2, 1. Last 5 rows. Please do not sit back there. Come up to the front. 6 rows, last 6 rows. Come on up, come on up. Okay, we lock up the vote. Count, look behind you if you're near the back of the room. Count up. If you get to 6 and you're in a seat or less, then come forward. Come forward. Okay. How'd we do here? Goes right, goes left, stays in the same place. Okay, so more or less, I think this is a vote of have you seen this before or not? So those of you who voted A got it correct. Once I did this in class, did they do it in Physics 112? It's a surprisingly large number of you have seen it before. They did it in Physics 112 this year? Yes? Who saw it at Cornell? Raise your hand. Okay. Once I gave this and somebody said it goes to the right. You're right. And I said, why? He said, because I'm pretty sure it goes to the left, he said, but I'm pretty sure that you know that I think that. And you wouldn't give this puzzle if that was the right answer, so it must go to the right, he said. So anyway, here's what it does. It goes to the right. Now, that does violate some people's intuitions. So the simple intuition is that you think of this as floating in space. You think of this force as having a torque about the center of mass. I just told you that it's always correct. Right up on the blackboard it says, if we want to figure out the rate of change of rotation, of the angular velocity, you look at the torque. This thing clearly has a positive torque in the counterclockwise direction, so it should rotate this direction. And that's what it would do, is it would rotate this direction if it was in space. But if you draw a free body diagram of this thing, there's a force on the ground here. and we don't know how big that force is. So that reasoning that says it must rotate this way is not correct reasoning, because it's not based on the complete free body diagram. Okay, is that clear what I just said? Any questions about what I just said? So we can't conclude from just the simple argument on the blackboard that this has a counterclockwise torque, therefore this must rotate this way, because that leaves out all the forces in the free body diagram, namely the one at the ground. If it did rotate this way, how would it accelerate? Let's say this was in space, not on the ground. What would it do? Well, we can simulate that situation by putting a large force on the bottom here. If we put a large force on the bottom, we will overwhelm the friction force, and it will do about what it would do if it was floating in space. And what does it do? It will rotate counterclockwise when I put a large force. And how will it move? Which way will it go? To the right or the left? All those who say to the right, raise your hand. To the left, raise your hand. I got you this time, huh? Okay, so why is that? Is because here we are in space. The only force on this thing is in that direction. What's the equation up there? It says F equals ma, right, top left of the blackboard. We always have that for all system all the time. The center of mass always follows F equals ma. So if you apply force in that direction, and that's the only force, or if that's the dominant force, then it goes in that direction. Is that clear? So it rotates this way, and it goes that way. The rolling constraint, not correct to think about the rolling constraint, because I had a big force that overwhelmed the friction on the bottom. Or I was thinking about this thing as being in space, so it goes like this. Any questions about that one? Yes?
If you pulled up at an angle, like at a high enough angle,
So certainly if I pull on it on this side over here, it goes to the left. And when I pull over here, it goes to the right. If I just tip this up a little bit, it still goes to the right. If I tip this up a little bit, it still goes to the left. Somewhere in between, there's got to be a switching point. Obviously, right? Where is that switching point? Let's see, if I pull it here, it still goes to the left. If I pull it here, it still goes to the left. If I pull it here, it still goes to the right. Can we figure out a simple way of describing what the switching point is? What angle is the switching point? A precise way of describing what the angle is where it switches from going to the right and to the left. Does anybody know? Say again? I can't hear.
I'm not going to answer the question.
Okay, well, I'll just leave that as a puzzle. Any time during the class anybody thinks they have an answer to it, let me know, and we'll see if I agree. Okay, so now we'd like to analyze this thing. What do we have to work with to analyze this? One thing is we have some basic kinematics. So what I showed you above is the general rules we have for any two-dimensional object moving any which way. If we want to make it a predictive theory, we have to have laws for the forces, so we can use our crystal ball to go forward in time. But whether or not we have laws for the forces, those equations are correct, constrained or not constrained. Now that we're going to talk about constrained things, we have to worry about the kinematics. What's the basic kinematics that we have to worry about is how different points on this object move. And the key kinematic relations that we have to deal with are, if we look at any 2 points, say R, B with respect to A, 2 points, and we look at the relative position between them, we have that the velocity of B with respect to A, by which we mean, that's defined as the velocity of B minus the velocity of A, is equal to omega cross the position of B with respect to A. And we also have that the acceleration of B with respect to A, by which we mean the acceleration of B minus the acceleration of A, is equal to omega dot cross the position of B with respect to A. But that's not all there is to the acceleration. That's the acceleration of this thing going this way if this thing is spinning faster and faster, if the angular velocity is increasing. We also have a centripetal term, which is this minus r squared of B with respect to A. So we have this kinematics to work with. all the time. Now we'd like to use this kinematics in this problem to figure out what's going on. Okay, just because it's a rule in this class to get free body diagrams out of the way, before I go to use the kinematics, let me just draw a free body diagram of this thing so we have it over and done with. It's nice to take a little bit of string or film or whatever and include it in the free body diagram so you're not confused about what's going on here. Just like with trusses, it's nice to cut the bars a little bit away from the joints. And we have this force here. We have this point G, and we have this mg force here. We have some force in this direction, N. In this case, it's going to turn out to be mg, but we can figure that out. And we have some friction force here, which I'm going to call F sub F. And just to make it so I don't have too many F's around, let me just call that a T. And I'll put in a dotted line here an X, and we have directions I and J. Now, can we figure out what's going on just from this free body diagram without this kinematics? We cannot. Because we don't know what this friction force is, and we can't find it easily. Why can't we just say that friction force is mu times the normal force? Why not? Yes?
Does the weight change that you
The weight could change if I'm pulling up at an angle, so that's one reason I can't figure it out. But let's say I'm not pulling an angle, I'm just pulling sideways. Then the normal force, whatever it is, the friction force, why isn't it mu times the normal force? Because it's not sliding. Friction is mu times normal force when things are, well, now it is sliding, of course, but in this problem as it's idealized now, it doesn't slide when I roll this, and unless it's sliding, friction force is not mu times the normal force. For example, friction is certainly important to keep me from falling down in this room, but is the friction force mu times the normal force when I'm standing here? No. It could be up to that big to keep me from sliding around, but right now it's not that. And even if you push on me sideways a little bit, it's not that. And nor is that true in this problem. And if we're going to assume rolling, we can't assume the friction relationship. All we know about this is that for rolling, Ff is less than or equal to mu times n, but probably not equal. Okay, let's see what we get out of linear momentum balance and angular momentum balance. Again, before we get into the details of the kinematics, linear momentum balance tells us that Ti plus T plus F of friction times I plus N minus mg times J equals the mass times the acceleration. If we assume that this thing does not leave the ground, it doesn't fly around, we can assume that this acceleration is equal to AXI. And then we can take this equation and we can take the dot product with I and J. So if we take this equation, even though we think of I as the simpler direction and J as the hard direction, let's just do J first. If we dot this with J, which is like looking at sum of forces in the y direction equals ma in the y direction, we get that n minus mg is equal to 0. And if we take the x component, or dot this vector equation with I, it tells us that T minus the force of the friction is equal to max. Now what do we have as unknown here? N is an unknown, F friction is unknown, AX is an unknown. So we have here two equations in three unknowns. We can't get the answer from this equation, and it's sensible that we can't get the answer from this equation because we haven't yet told this problem that this thing is rolling. And we get a different answer if it's rolling or if it's sliding or if it's in space. And so far, the equations don't know the difference between those problems. Is that clear? Yes.
Why is it T cross the force of friction in the first line and force of friction in the last line?
You're not allowed to ask questions like that. Can you please rephrase the question?
I'm not sure. Should it be T plus force of friction in the bottom line?
Yes.
Okay. I wasn't sure if those signs.
Okay, why do you go to Cornell as opposed to Southeastern Tennessee, Kalamazoo Junior College? It's because you're supposed to build up self-confidence and arrogance and stuff like that, and you should practice that in the way you ask questions in class. So you learned something today. Okay, how many degrees of freedom does this problem have? When we started talking about the eraser flying through space, we said it had 3 degrees of freedom. It could have a free x coordinate, a free y coordinate, and a free theta. And this problem, we assume rolling, how many degrees of freedom does this thing have? 1. All that we need to know is how far it moves sideways, and the x and the theta are coupled to each other. If we know one, we know the other. This only has 1 degree of freedom. Okay, so now we want to start getting into the kinematics and figuring out what's going on here. The main thing we need to figure out is what's the relationship between theta and x, or between omega and vx, or between omega dot and the acceleration in the x direction. So the key to this kinematics is we're going to look at 2 points here. I'll call them C and C prime. And this is a point of contact. So this is how we work out these rolling problems. Kinematics of rolling. We use the great Laurie Anderson result. I think I promised you in 202 last semester to play you the Laurie Anderson tape, and I never did. And it's right here on my computer, so I'll try to cue it up next time. So what we're going to use as this great result is that the velocity of point C is equal to the velocity of point C. And as I think I've said before, this is the equation you use to solve almost every problem, that you take something and you think about it 2 different ways, and then the math tells you how to equate things about those 2 different ways. So one way of thinking about the velocity of C is that it's the velocity of C prime, which is 0. Why is that? It's because if we look at this point on the bottom here, see that black dot there, and we compare it to this C prime here, as this is rolling, that black dot is not going to the right, and it's not going to the left, and it's not going up, and it's not going down. That point on the bottom, not for all time, but just at the time that we're looking at, that point on the bottom has 0 velocity. It has the same velocity as the point is touching. That's what you mean by rolling as opposed to sliding, is that it's got no velocity this way, and rolling as opposed to penetrating or flying away from, it's got no velocity up or down. Okay, so that tells us that this thing is 0. So we're going to have 0 down here. On the other hand, another way to think about the velocity of C is that it's the velocity of G plus the velocity of C with respect to G. Where is C? It's where G is plus where C is relative to G. How fast is C moving is how fast, or what velocity does C have? It's the velocity of G plus the velocity of C with respect to G. So now we have 0 here. This is what we would call V, G, X in the I direction. That's that term. And what's the velocity of C with respect to G? That is omega cross the position of C with respect to G. Now we can fill in this omega. Omega is equal to omega dot K. This position of C with respect to G, R of C with respect to G, is equal to the radius of this thing in the minus j direction. So somewhere here we have to put in a radius. So then this tells us that 0 is equal to vgx I plus omega dot k crossed with minus rj. Sorry, omega k. There's no dot here. Any questions about that? Yes?
What did you write VC prime on the left?
Why do I write VC prime? Is I said this is the rolling constraint. The rolling constraint is that the point on one object has the same velocity as the point on the other object at the point of contact. And that's the C and the C prime. This is C. This is C prime. Does that answer your question? Okay, now we can do these cross products. Here's VGXI. This is K crossed with J. K crossed with J is minus I. But we already have a minus here, so this turns into plus omega Ri. Now we take this equation and dot both sides with I. And it tells us that VGX is equal to minus omega R. Okay, let's see if that makes sense. Omega we're taking as positive in the counterclockwise direction. So if this happens to be rolling this way, omega would be negative. And what's the velocity of this thing is positive. So the forward velocity of this middle point is minus omega r, which you could get intuitively just by looking at this thing. But now we've got a way to do these things more carefully. Now, when I did that derivation, I didn't use anything about where we were in this process. There was a roll of paper towel around here somewhere. Where is it? So that equation that I wrote about relating velocity to omega is an equation which is true at all time, not just at one instant in time. Therefore, we can take the time derivative of it. It's something to be careful about in dynamics. Sometimes we write equations which are only valid at one instant in time, and sometimes we write equations which are valid for all time. And you have to keep track of which is which. This one is one which is valid for all time, assuming that it's rolling, so we can differentiate it. So we take that equation. What number did I give it? 1. 1 is valid at all time. So we can differentiate it. And what that tells us is that acceleration of g in the x direction is equal to minus omega dot r. Okay. Any questions so far? Now we can try to figure out the motion of this thing. Let's go back to that free body diagram. And since this only has 1 degree of freedom, maybe we can find one angular momentum balance equation which will tell us what we need without ever having to find that friction force F. If we don't know it and we don't care about it, we try to get rid of it somehow. how can we get rid of it? It's instead of using angular momentum balance about point G and ending up with 2 equations and 2 unknowns, or 3 equations and 3 unknowns, we can just get right to the point. So let's just do that. If we take angular momentum balance with respect to point C, it says the sum of moments relative to point C is equal to H dot relative to C. We could use point G, but then we'd have to solve 2 equations and 2 unknowns. Why only 2? Because N we can figure out is equal to mg just from this equation. So the only 2 unknowns are the ones relating this tension and acceleration. Okay, what are the sum of moments with respect to C? Well, we have this tension force multiplied by its lever arm, which is R minus R. So I've got to put in another dimension in here. Besides this capital R, I need a little r here. Which is the radius of the film as opposed to the radius of the spool. And that gives a moment in the minus k direction. And what's the h dot? We have the position of g with respect to c crossed with the mass times the acceleration of g plus ig omega dot k. Now, this would be true whether it's rolling or not. If I want to put rolling into this problem, the way that rolling shows up in the problem is by eliminating one or the other of these 2 variables. So remember that we have that the acceleration of g was equal to agxi, and we have this relationship between agx and omega dot, so we can eliminate one or the other of these 2 expressions, one or the other of these 2 variables. Let's eliminate the omega so we can figure out whether this thing goes to the right or to the left. So to eliminate omega, where we see omega dot, we put agx over r with a minus sign. Okay, so that means we have on the left-hand side t times r minus r times k, and that had a minus sign. And remember, the whole question I asked you, the whole puzzle problem was to the right or to the left. It was a whole problem about signs, so we can't say we got it right but for a sign error, because that means we got it wrong, right? Because we're actually asking whether it goes to the right or the left, so we're trying to do all the cross products and all the signs carefully, so we actually get whether it goes to the right or the left. So we want to try not to make any sign errors. Okay, then we have this position of g with respect to c, which is a positive rj. Then we have crossed with m agxi. And then we have plus ig, and where we had omega dot, we can put minus agx over r. And then this gets multiplied by k. Now we have to do this cross product. And then we can combine terms. So on the left-hand side, there's not much we can do with that. Minus t r minus r in the k direction. On the right-hand side, we have a j crossed with I. J crossed with I is what? One, two, three. J crossed with I is? Okay, so we have a negative k, which gets mixed together with this negative k. So we have 2 negative k terms. We have a r, m, so we have r, m, and agx. And we also have a plus an I, g, agx, all over r. And this is all in the negative k direction. Oh, sorry, I was on the other blackboard anyway, wasn't it? Okay, we have negative something times k. And that negative something times k was an rm agx. And it was a plus ig over r. Okay. Now we take this whole thing. What? AGX. Now we take this whole expression and we dot both sides with k, and we get minus t r minus r equals to, then we have an AGX which pulls outside this whole thing, and then we have an RM plus IG over R, and this thing had a minus sign, this thing had a minus sign, so we can get rid of both of those two things, and we have then that AGX is equal to something times T, and what is that something? It's an R minus R divided by RM plus IG over R. So we get an acceleration to the right depending on what this tension is. How big is that acceleration? Let's say R is very close to R, little r is close to big R, it's not very big. Why is that? It's because what's really driving this thing is the lever arm of this force relative to this point. So a way to think about this problem in disguise is that this problem is the same as, now we need some stick, some large stick-like object. This problem is the same in disguise as taking this problem, leave gravity out, imagine that it's hinged at the bottom, and I apply a force sideways right here. So if I apply force sideways to this ruler right here, what does it do? It accelerates in that direction. What's the acceleration of this point here? It's given by the same formula we have for this one. What's happening is that I'm pushing here, and I'm getting a translation of this point, and I'm getting a rotation of this object. So in disguise, this thing is as if it's hinged at this point, and it's accelerating that way. So I get an acceleration due to this small lever arm resisted by all this mass up here. Okay, so that's the problem, that's the answer. Any questions about it? Okay, I've got 2 minutes left, which I'd like to use just to set up the beginnings of a sort of harder problem. Let me show you the beginnings of a harder problem. Let's just say I have a cylindrical bowl, and I have a round object, a ball, or a movie about the heat treatment of aluminum, rolling inside that bowl, and I would like to keep track of how this moves. So what I'd like to do in order to keep track of how this moves is I will keep track of where is the center of this thing. So we have the center of this thing, RG with respect to O, but we also have this contact point. So we also have this C and this C prime. The key to figuring out how this problem works is to figure out what is the relationship between, say, this angle here, theta, and this angular velocity of this object here. How can we figure that out? We can figure it out by saying that the velocity of C is equal to the velocity of C, and therefore we can say 0 is equal to the velocity of G plus the velocity of C with respect to G, and therefore we can say what's the velocity of G? Well, the velocity of G is given by, if we take polar coordinates here and call this ER and call this E theta, the velocity of G is given by this radius here, I'll call this R, I'll call this little radius little r, it's given by R theta dot E theta, whereas the velocity of C with respect to G is equal to omega of that object, which is omega k, crossed with R times ER, which is the position of this thing, is the position of C with respect to G. So this then gives us a relationship between theta dot and omega, and from that, that's true at all times, you can differentiate to get a relationship between theta double dot and omega dot, and from that, if you say we're doing this in the middle of the mechanics problem, you could plug this into the angular momentum balance equations and figure out how this thing moves. Okay, any questions? Too fast? Yes, quick question. Go ahead, ask the question.
Why is there a big space between the rest of the terms and T?
Why is there a big space here? I know, I thought it would be a bigger expression. The answer to the puzzle question, by the way, what's the angle at which you pull this that it doesn't know whether to go right or left? It's when the line of this tension force passes through the ground contact point, and so it has no moment arm. So if you look at the geometry of this and look at this line here, when this angle is such that it goes through the contact point, there's no moment arm, it doesn't accelerate right or left.